What's going on, guys? Today I will walk you through how hackers actually exfiltrate data, what telemetry you should care about, and the exact detection steps SOC teams use to catch them. And that's all drawn from TryHackMe rule named Data Exfiltration Detection. So let's get started. Data exfiltration, simply put, is an unauthorized data leaving your secure network, secure device, secure host, whatever you want to call it. It is not just about someone copying a file, it's a strategic adversary objective. Monetize, gain intelligence, or extort. That's the ultimate objective of data exfiltration. Hackers will often follow a predictable life cycle. It starts with discovery, then it moves on to staging, egress transport, and then verification via C2. A single alert rarely proves exfiltration usually, right, in SOC environment. Effective detection means correlating host telemetry like processes and command lines, network telemetry like flows, proxies, DNS, and of course, cloud logs if applicable, of course. Your first triage should answer 5 questions. Who initiated the data transfer? Where did it go? How much data? Which process did it? And what corroborating logs exist? Hackers actually love existing network channels. For example, HTTPS uploads to cloud storage. That's one method they use to exfiltrate data, maybe through FTP or even tunneled protocols like DNS or ICMP. You should watch for large HTTP posts to personal cloud accounts, maybe even long duration flows to single external IPs, or even frequent high entropy DNS queries. Basically, on the host or on the compromised host, let me say, living off the land binaries are the go-to for data exfiltration. Think of PowerShell, Curve, wget. These tools are extensively used by attackers to perform data exfiltration and stay off the radar. You should monitor process create events, network connect events, and command line arguments. They're gold for attribution. If hackers use cloud buckets as the destination, as we always see most of the time, you should look also for unusual API keys, anomalous uploads to S3 buckets. Here I'm talking about AWS services, and of course, misconfigured service principals. Correlate cloud audit logs with user activity all the time. Now let's talk about covered channels, and here I mean DNS and ICMP. Covered channels like DNS tunneling or ICMP tunneling are actually stealthy because they ride protocols often and most of the time allowed by firewall rule sets. DNS tunneling encodes data inside subdomain labels or text records. At the same time, ICMP can carry payloads in ping bodies. We call them ping requests and responses. Usually, detection relies on statistical signals, as you will see in the practical scenario, like unusually long host names, lots of text queries, or high entropy in query strings. Okay, to start the investigation, in Splunk, first we set the index. The index here happens to be data underscore exfil, which is the index that's hosting all of the logs data that have been ingested to Splunk previously. The next thing we want to do is to specify a source type. Here, the available source types we have are sysmon logs, HTTP logs, and DNS logs. Since we're investigating DNS logs, we want to specify DNS logs as the source type. So we type it here, and we can see now the number of events shows 2,000 events, 2,000 DNS requests and responses. Now, to identify data exfiltration attempts, we want to find out what are the source IPs sending the highest number of requests or DNS requests. That would give us one indicator. To do that, all we have to do is to use the type and then use another command. This command will sort the IP addresses based on the number of DNS requests that have been sent. So basically here the components, or we can use the stats function followed by count to sort them, and we will specify the source IP as the field. You see, the source IP here is an already existing field on the left. It's not something I came up with. So it's basically here, source IP, and it shows the IP addresses. We see if we click on this, we already have a view on the number of IP addresses, or the IP addresses sending the DNS request. We see the count beside each IP address. But you also want to take advantage of the stats function in Splunk. So use stats count by source IP. Okay, we notice that the IP address 192.168.1.1.1 is sending the most number or the highest number of DNS requests. We have around 406 DNS requests. Now, if you go back and drill down on this IP address, so we click back on the source IP addresses, we click on the source and we identify the IP address. It was 1 point. Let's go back. Actually, I think I forgot the IP. Stats count. Let's go. Yeah, that's how it's supposed to be. It is 1.04. I forgot to sort them in descending order. So now after sorting them in descending order, you see the highest number of data requests is 413. And it refers or it points to the IP address that ends with 104. So now we go back to events. And here we specify in the query source IP equal the IP that ends with 1.104. So now we have the number of DNS requests is 413. So you see now we identified the IP address that is possibly used for DNS data exfiltration. However, we still have not pinpointed the domain name that is receiving the DNS requests. So here comes another indicator, which is suspicious looking DNS domains. We want to find out what are the domain names that are receiving the DNS request. So basically, to do this, we're gonna have to run a different sort of query here. This time we're gonna I'm gonna use this query and I'm gonna explain how it works. You see, I'm still using the DNS logs, okay? And again, I'm back to stats count to sort the queries by the count, okay? So now we see all the DNS queries sent. So by using query, we are able to see the domain name, okay, that is receiving the DNS queries. Among the domain names, we see suspicious looking domain names, or maybe these are actually queries. The base 64 here, or the weird looking strings, these aren't base 64, some of them. However, these are suspicious looking queries followed by the domain name, which happens to be tunercorp.net. You see, we have single request. For every query, we have a single DNS request. The other DNS requests look perfectly normal. Microsoft, Stack Overflow, Wikipedia, and GitHub. So now we identify the domain name that's possibly the domain name responsible for receiving the DNS data exfiltration. This means that this domain name is the C2 domain that is now actively receiving the data being stolen from one of the hosts. And now if we go back to events, okay, and now we click on the query field, you see now we are able to see the queries, right? Still, however, we want to find out which IP address is responsible, or which IP address is the IP address from which all the DNS queries are being sent. Because if we are able to identify the IP address, it means we will be able to identify the compromised host from which the data is being actively stolen and exfiltrated to this domain name. So to pin down the IP addresses, all we have to do is to include the suspicious domain name tunnelcorp.net in the query, in the Splunk query. So basically here we can use two asterisks, and in between them you can use tunnel corp. This will retrieve all the DNS requests, or maybe all the DNS logs where tunnel corp is involved. So clicking search, and now we have around 315 events, which means we have 315 DNS transactions to and from tunnel corp. Okay. Now what's important for us in the investigation is to pin down the IP addresses. So basically here we have 103 with 72 count to tunnel corp, 105. Basically, all the IP addresses here we have on the list are exchanging DNS transactions with tunnel corp, which means they are compromised. So that's how we identify the compromised hosts that are sending DNS data to C2 domains. As always, when we want to use Wireshark to detect data exfiltration attempts through FTP, we want first to have a look at the FTP sessions. Here you can see all the FTP sessions that were recorded during the exfiltration attempt. We want to find out, or we want to spot which was the account that was used to exfiltrate data from the host. By the way, to look at the FTP sessions, all I have to do is to apply this filter. So basically, I'm going to apply this filter again, FTP, double pipes, FTP data, and then you can see we have all the sessions recorded. Now, after doing that, we might be interested to spot the commands that were executed by the attacker. Among them is user and pass. So this will show us any possible suspicious usernames or passwords that were passed. You see the use here of user command or pass command. All right, you see now we have a look at the usernames. We have dev, we have test, And also, if we scroll down, we might stumble upon other users as well. For now, I see only dev and user, and probably I see test. I saw test here, so test, user, and dev. And looks like that is just it. So when you spot a suspicious user that is not created by you, all you have to do is to investigate it further. So if you assume that you see the user test for the first time, you're gonna all you have to do is just right-click and follow the TCP stream. Now, sometimes if you want to skip directly to what are the files that might have been exfiltrated, you want to apply this filter. FTP contains, and here the example is CSV. This will spot all the CSV files that were exchanged from and to the FTP client. You see now we have 4 events or 4 packets that include the CSV file. And if we bring this up a bit, the first packet shows the user root. And if we expand this, have a look. So the file that has been sent from the IP address 101 to the external IP address 185.203.119.12, the file name is internal passwords. So now we spotted one of the files that has been exfiltrated. If you look at the other one, through the use of guest user, a file has also been exfiltrated from the IP address that ends with 105, which happens to be an internal IP address, to the same external IP address. You see, you have the same external IP address across all the 4 captures, which means packets, which means that this is the C2 IP address of the attacker. And by looking at each packet, we can see the files that were exfiltrated. So here we have passwords, internal passwords. Then we have again internal passwords. Here we got a flag. Probably going to use it to answer the questions. And then we have again internal passwords. You can change the extension, by the way, depending on what you're looking for. You're looking for PDF. So we have 0 packets, which means 0 PDF files were exfiltrated. Also use XLSX for Excel files. You see we have customer data as well, exfiltrated from 103 to the same attacker's C2. Along with the file, we can see the username and password that have been used in the query. So here, guest and guest. The other one we have root, and the password is Tor. So using these filters, you'll be able to spot any data exfiltration attempts. How many connections were observed from the guest account? So basically, now we're looking to investigate the guest account. A cool, easy method to narrow down all the packets to those involving the guest account is to use a Wireshark feature that includes the ability to sort using the columns. So Wireshark.column, and my column here is info. I'm looking at the info column here, and what I want to specify is the double equal sign, request user has to be guest. So now you see we have 4 packets. No, 5 packets. The answer is 5. Apply the filter. What's the name of the customer related file exfiltrated from the root account? We have already seen this in the previous filter. When we applied the file filter, we saw there was a CSV file, maybe. It was Excel file, the extension XLSX. And here we see the file name is customer underscore data. Now the next question is, which internal IP was found to be sending the largest payload to an external IP address? Now, since here numbers will be involved, we want to now use the statistics feature in Wireshark. So basically, all we have to do is to go to stats and then resolved IP addresses, or maybe conversations. Okay, so we're looking for the largest payload sent to an external IP address. We sort using the bytes or the packets. We have 4 packets sent from the IP address 103 to the external IP address 185. So the IP address we're looking for is not necessarily 103. Yeah, I know 103 has the highest number of packets sent, but you see, the IP address 105 sent only 1 packet with 87 bytes, which is approximately 50% of all the packets. This means that if the IP address that ends with 105 has sent the same number of packets 103 sent, it would have been much larger in size than the packet sent by 103, which means that my IP address here is 192.168.1.105. And lastly, what's the flag hidden inside the FTP streaming, transferring the CSV file? Now we go back. I think I closed Wireshark inadvertently, so I'm gonna reapply the filter, contains CSV, and from there we extract the flag. So that's our flag. It doesn't look good. Let me check. So copy all visible items. Let me fix this. In investigating HTTP data exfiltration, we want to look at specifically the post requests, because the post requests are the requests sent when there is data involved in the process. When an attacker uploads data, even when you upload data to a server, you send a post request. So for an attacker to exfiltrate data from the victim machine to the suitor machine through HTTP, they have to do it through HTTP post requests. That's why in our query here in Splunk, first we have specified the index, the source type happens to be HTTP logs from here, and we have to specify the method. The method here should be post requests. In total, we have around 3,075 requests or post requests sent or spotted in the logs. The next thing we want to do, we want to find out what are the requests which happen to be large in size, the large request size, because usually when there are files uploaded from the victim machine to the attacker machine or the attacker C2, these files come actually in moderate to large sizes, speak of more than 1 megabytes. This will exaggerate, or maybe this will enlarge the request size. That's why we should look for the post request with larger size. Therefore, I'm going to copy the long query from here, and then I'm going to explain it. Okay, so what do we have here? You see the same query. However, I pipe the query or the output of the query to a stats function. Stats count, and then we have the average function, which calculates the average byte sent. And also calculates the maximum bytes, the minimum bytes, and do all of that, or sort all of them using domain or by domain or per domain basis. Okay, and sort them in ascending order according to the count. You see now the highest number of post requests sent are to api.tools.io. This does not mean that this is a C2 domain, right? However, it is good to find out, or it is a good practice to sort them and find out what is the domain name that received the highest number of post requests. Then we have here the maximum bytes sent, which happens to be 450 bytes. Again, it is addressed to api.tools.io. You see, if you continue doing this, we will be able to have statistical analysis about the post requests sent to each domain, but we want to filter the noise, or maybe put the good guys aside. That's why we're going to have to tune down the query a little bit further. Therefore, I'm going to copy the new query from here. This new query, it will actually use the bytes sent and specify a threshold. This is the threshold above which I start to suspect C2 traffic. You see now all of the requests sent here, they are classified with an average size of, you see, 372 bytes sent. These represent the baseline network traffic in my environment. Okay. Now, when I go above 375, maybe above 500, as specified here, this means that I have an abnormal or deviation from the baseline. Still, it could be something benign, not necessarily evil, but I want to find out what it is. That's why I specify bytes sent. It has to be more than 600. Okay. You could also specify this 500. The value is determined first by looking at the average bytes or the average size of the bytes sent. Okay. The maximum here points to 450. Yeah, I know I have 654 here. However, here I'm looking at the average. So here I'm going to choose 500 and then use table to sort the results based on the time, the source IP which sent the request. I want to find out what is the IP address, the domain name, and the destination IP address, which will reveal the C2 domain if there is, and of course the bytes sent. And of course, I'm going to sort them using the source bytes sent, which will give me the descending order of all the bytes. So executing this query here, you can see we have only one domain name or only one request where the bytes sent happens to be more than 500. If you look at the characteristics, we see the source IP ends with 103, And the request URL here, this is the URL that was used to upload the data. Remember here we're dealing with HTTP data exfiltration, which means the attacker will have to manually, not necessarily browse, but maybe use a curl command and specify the URL to which the data or through which the data will be uploaded. And that's the main domain, and that's the destination IP address. Now, if you look at the domain name, it doesn't look suspicious, right? However, this represents a deviation from the baseline I have in my environment, sending a large request or post request. Specifically, it happens to be upload, right? Which increases the chances of this being a data exfiltration attempt covered by a benign looking domain. API Cloud Sync Services, right? It doesn't look suspicious. However, it doesn't look benign either. Cloud Sync Services. Anyone can acquire such domain. Now, still, this is not the end of the investigation. Maybe we have to correlate this with other SOC tools like Wireshark. So we're going to keep this as is and maybe pivot now to Wireshark. So the Wireshark now here we have the packet capture imported to Wireshark. Now we use HTTP filter to find out or to filter or to narrow down the packets to only show the HTTP packets. Next thing I want to do here is to show the post request. You see now I have all the requests, get, post. I want to narrow down these to only show post requests. So here I use the filter http.post.request or method, request method happens to be or should be equal to post. Now I see all the post requests sent to all the IP addresses on the cloud. That's also not enough. Remember, in Splunk, we learned that there is the suspicious C2 domain, or could be C2 domain, that's receiving the post request from the IP address with 103. You see now the bytes sent is, or more, it's more than 500. So maybe if we go back to Wireshark and use frame length filter. So back to Wireshark, I believe here, and use end from here, frame length more than 500. Taking a closer look now, we see that we maybe have narrowed this down, but not enough, because we still have large number of packets. So probably here we're going to have to increase the frame length more than 500, maybe 600. And this only shows now one request. Again, from the IP address 103, the same IP address we saw earlier in Splunk, and the same path /v1/sync/upload. Right click, and maybe we use follow TCP stream to have a look at what has been uploaded exactly. So here's the request, it's post to the exact path we talked about, and we have the parameters sent with the post. We see we have the username specified, because at the end, if you want to upload data to a server, you can have to be authenticated. So these are the credentials the attacker used to authenticate maybe to their server, and we have SSH key fingerprint, and at the end, we can see the flag. Now, because we're doing a CTF scenario, we see flag, but usually you should see files here. Also, we have file hashes. Look, we have secret to text, backup. This will actually allow us to write a report with all the exfiltrated files through this HTTP request. Now, if you go back to the questions, which internal compromise host was used to exfiltrate the sensitive data? It is the host that ends with 103. So it is 192.168.1.103. And what is the flag? I guess this should be easy. Or without right-clicking or going to TCP stream, you can just drill this down and click on data, expand data, and here you can find the flag in the hex view. However, you can still go back and follow TCP stream and copy the IP, the flag. And the last thing we want to look at is data exfiltration through the ICMP protocol. As you know, ICMP protocol is a protocol used to test whether a host is live or not. However, it can be used for data exfiltration as well. The first thing we want to do when we have a packet capture, and we want to drill down all ICMP packets, is to use the ICMP filter. This will give us all the packets where the ICMP is used. Basically, the ICMP echo requests and ICMP echo replies. The next thing we want to do to spot data exfiltration attempts is to look at ICMP echo requests. To do that, you can use ICMP.type equal 8. This will give you all the ICMP echo requests. As you can see, all I see here are ICMP echo requests. All right, the next thing we want to do here is to figure out how to add another filter to spot data exfiltration, usually through ICMP request and also many other RISE protocols, the large size of the payload or the packet is the red flag. So when I have frame length more than a specific size, it is actually a red flag. In ICMP, we can use, much like in HTTP, we can use the frame length. Now, the value here is actually dependent on your environment and the packet capture. Okay, usually anything more than 75 is a red flag. Not necessarily above 75, but we start from the value 75, and then we actually filter until we get the correct packet that has the exfiltration attempt. So now we have around 6 packets where the byte size or the frame length is more than 75. If you look at these packets, you see all the packets originate from internal IP addresses. Okay. Among them, we have this one. The length of the packet is 79, or the frame. If you take a look here, we can see the file is, or it looks like the file is a compressed file, but it's not clear what kind of file is this. It could be an exfiltration. And then we have the other packets. Their length is more than 79. It's way, way more than 75. It's 148. If you look at one of them, specifically the one that originates from the IP address 103, we see here on the right the data, and among them we can see a flag. Also, we can see the files that were exfiltrated. We can see secret, or we can see backup. These were the files that were exfiltrated. Now, if we drill down here, you can see the data bytes, 120 bytes. And looking at other packets, so the IP address that ends with 101, we can see username and passwords. 102, SSH key fingerprint. Now, the one that matters is this one, 101. Sorry, it is 103. It is where we can see the flag and the exfiltrated files. So this was it. Now let's answer the questions. There is only one question here, which is the flag, and that was it. Now, here is a practical SOC playbook you can adopt and modify depending on your environment to triage an exfiltration attempt. Start with containing the host. Use methods like snapshot, isolating network ports, preserving volatile logs. That's the first step. The next step, identify process and command line. Find the exact binary and its arguments, like PowerShell with -encode command or Rclone sync. These are considered as smoking guns. The third step in your playbook is to map the destination. For example, resolve domain names, ACNs, and geolocation. You can also check proxies and next-generation firewall logs for matching flows. The fourth step will be measuring volume. And here we're talking about NetFlow and proxy bytes. Usually large anomalous outbound byte counts means high severity, which means you should carefully look into it. The fifth step here is cross-corroborate all the time between tools and logs. And think of DNS logs, EDR alerts, cloud audit logs, and email logs, web proxy logs, correlation logs. You have always to correlate to build a solid case. The sixth step here is forensic capture. Make sure to collect memory, process dumps, and a full network p-capture if it is possible. And the last step is start hunting for staging. Check for large archives, recent zips, or encodings on hosts and network shares. Just remember that backups these days are not enough. Why? Because ransomware or modern ransomware uses double extortion. It exfiltrates data first, and then it doesn't stop. It encrypts the existing data. So, backups stop encryption losses. However, there are other losses like reputational or regulatory damage from data leak. These losses cannot be stopped using backups, right?